All right, let's do this starter here. It involves a little bit of momentum, a little simple harmonic motion, even a little energy. So this is a good problem because this is kind of what you'll get on the AP test. They like to have 2 or 3 different concepts in one problem quite often. And so here's what we got. We have a 5 kilogram mass here at rest attached to a spring with a spring constant of 300 newtons per second, or newtons per meter. And this other cart, it's also 5 kilograms. It's coming towards it at 2 meters per second. And they collide. And when they collide, they stick together. So there's little magnets. I try to draw. It could be Velcro or magnets or something. So they're going to stick together and then oscillate like a simple harmonic oscillator after they stick together. So the question is, A, how fast are they going to go just after the collision? B, what is the angular frequency of the system? What is the period for one oscillation? And what will be the amplitude of this oscillator? Okay, so go ahead and pause the video. And when you're done, unpause it and check your work. Let's do part A. So now, part A, it's just like we want to know how fast are they going just after they collide. So this is purely a momentum problem, and the easiest kind. And that's what you're going to get on the AP test. The AP test problems are really actually pretty easy. They're sometimes just kind of like disguised. So you have to, if you can see through their disguise, you'll see that, oh, this is very doable stuff. So in a collision, the initial momentum of your system is equal to the final momentum of your system. And if I go off screen, I want group 9 to tell me. Okay.
Yes.
All right. Now, the initial momentum, well, where's all the momentum? Before the collision. Well, this one's not moving. It has no collision. But this one is. So that's going to be 5 kilograms, mass times velocity. And it has an initial velocity of 2.0 meters per second. Now, after the collision, just after the collision, it's 5 plus 5. We've got a mass of 10 kilograms. And they're moving together, so they share a same final velocity. So when I solve for it, it's just 5 kilograms times 2.0 meters per second divided by 10 kilograms. The numbers cancel here. 5 divided by 10 is 1/2. 1/2 times 2 is 1. So it'll be moving 1 meter per second just after the collision. That is my answer for part A. Part B. Well, you kind of have to just know this or have it memorized, but the angular frequency for a mass spring system, omega equals what? The square root of K over M. And one of the things, like sometimes the square root of M over K, I think that's for the period, but if it's the square root of K over M and you can't remember, you can get the per seconds from the newtons in the spring constant. And I'll show you how the units work out here in just a second. So the spring constant, it takes 300 newtons of force to stretch it or compress it 1 meter. And then the mass, oh, well, that's 10 kilograms, because the combined object is what's oscillating. And when you do the math, I already did the math. You plug that in, you get 5.48. Is that right? 5.48. Now, what should be the units here? Well, let's take a look at this. Newtons per meter per kilogram. Well, what's a newton? Oh, I'm off screen. Oh, you guys got to tell me. Kilogram meters per second squared per meter per kilogram. Now, the way this cancels out, the kilograms cancel, the meters cancel. You have 1 over second squared. We're going to take the square root of that, and you get 1 over seconds. Sometimes you'll see it written that way. That's okay. I'm going to write it like this, though. Radians per second. right? A per second is a second to the -1. Radian is a ratio of a length to a length that's really dimensionless, but I like to leave it in there. Does that make sense to everybody?
Yes.
All right. Now, the period is related to the angular frequency. It's 2 pi over omega, and you should know that. You should memorize that or put that on your equation list. Now, here's why. Well, what have we got? We've got omega, so that's 1 over, and what is this going to be? This is going to be 5.48 radians per second. See, the seconds are now up on the top. But what is the period? Period isn't time per radian, it's time per cycle, or time per revolution, or a complete cycle. And there are 2 pi radians in one cycle. That's why the 2 pi is there. So the radians cancel, although they're dimensionless. So it's kind of weird to say they cancel. And then when you go 2 times pi divided by 5.48, trust me, you'll get 1.15 seconds. Am I right?
Oh, yeah.
Right on. So this thing is going to oscillate once every 1.15 seconds. Part D. Now, the thing about amplitude, the thing to remember about a simple harmonic oscillator is that when it's at its maximum amplitude, all the energy in the system is now compressed in the spring. It's all elastic potential energy. But right after it hit, the spring wasn't compressed yet. And so all the energy was in kinetic energy. So all that kinetic energy after the collision will be equal to the elastic potential energy in the spring. Because once this thing gets going, we're going to assume it's an ideal simple harmonic oscillator. It's not going to lose any energy to the environment. Or we're going to pretend that that's true. So the energy, the mechanical energy it has initially, now initially I mean after the collision, because this has a lot of kinetic energy over here. I'm sorry, over here. This thing's got a lot of kinetic energy. After it hits and sticks, it doesn't have nearly as much kinetic energy. But it's the kinetic energy it has after it hits that squishes in the spring. So that's what you have to use. Well, E initial was 1/2 mv squared. And then E final was the energy stored in the compressed spring, which you should know. Now it's 1/2 k x squared. But really, since it's the x is at its maximum, instead of x, I'm going to erase that x, and I'm going to call it A for amplitude. And that's what we're going to solve for. So this goes away. I'm going to solve for V. So V is equal to, oh, wait, no, I'm sorry. I'm solving for A. So we'll solve for A. So A is equal to, well, I'm going to divide by K, so I'm going to have M over K. I'm going to take the square root of that, and then I'm going to take the square root of both sides, so that's just going to be V. So the amplitude is going to be equal to square root of M over K times the speed. So, well, M over K is the reciprocal of K over M. So we'll just divide, so we'll just say that this is V 1.0 meters per second, and then I'll divide it by the square root of K over M, because that's 5.48 radians per second. So the per seconds cancel. I'm left with just meters, which is what the amplitude should be measured in. And so when we do that, 1 divided by 5.48, we get 0.18 meters, or 18 centimeters. And that's my answer for part D. So let's zoom out a little bit, take a look at the whole problem. This is a really nice problem to study because there's a lot going on, but it's not none of the individual things are that hard, and that's what the AP test will be like. Some of it will be kind of weird, but some of it will be at this level of difficulty or less. So conservation of momentum, because we have a collision, simple harmonic oscillator, angular frequency, period, and all that. And then once it's oscillating, you can use conservation of energy. And that's one way to do it. There's another way to do part A. You can talk about, I think the maximum V max was equal to omega A. This is another basic equation, both for simple harmonic motion, and I think it worked for, I think it was omega R for rotational motion. They're mathematically very similar. So if you solve for A, you're going to get V max divided by omega, which is exactly what we did. Any questions? That is all.